Testing, testing. Okay, I think we're live. Whew, that took me way too long. Hello world. Good time of day. Whether it's whatever time of day or night, could be that as well. I saw this adorable chat a minute ago. I really should update my emotes. Thank you. Okay, are we live anywhere? Or did it just all end? 'Cause that could be the case. Okay, we're live somewhere. That's good. Alright. Hi. Hi. Is Coffee Cafe here? Yes, they are. Yep, seems like it. Whoa, it's been a while. Okay. Yeah. Life. Fun. Just wanted to be here, even if it's just for an hour. Some learning. It's just getting back to it, you know? Are we too big, too small? Should we change our size? Maybe go to this side. Yeah, we're fine. Okay. How are you? How's life going? Mine is just, life. Content. Content. That one was like a compulse video. I was like, this is fun. I want people to know about it. Put it out. That was the thought behind it. Took me like 2 hours of like editing on my phone, which like doesn't look like. I had to cut out the empty parts and add subtitle, which was I used Cut something. There's a really cool app that does that. So yes, there was content somewhere that I put out, which was actually pretty fun. Okay. Oh shoot, what was that? Why did I do that? I think I was. So I was thinking where I was. Hi. So I was in lesson 10, not 11. Oh, I updated the title to say lesson 11. My bad. I should not do that. I thought it was in lesson 11 for some reason. I have lesson 11 opened here, so that's why. I do remember trying to run the code and failing. Oh, that's changed. Failing miserably. Hold on, this has changed? No, this is wrong. And they changed it. There we go. Okay, this is the right one. Yeah. I tried running the code. I failed. I'm sorry. I currently don't have the energy to do that. I have the energy to be here and like listen to videos. That's all the energy I have. So I do apologize if you're here because you thought I might be working with the code. don't have the energy right now. Okay, I'm gonna do the intro that I should. I am here to continue lesson 10 of the introduction to machine learning for coders, a class taught by Jeremy Howard on the fast.ai platform. And yeah, it's 12 lessons. We're here. We started back in September. It's the first day of December, if you can believe that. And my brain was like, you're gonna stream every day December. And I was like, let's try. Don't believe in me, but let's try. So I'll try. They'll probably be shorter streams because I'm too lazy. Yep, there we go. I said it.
Rerun.
I could have been here an hour ago. I didn't. Okay. I feel like going back, honestly. Yeah, I'll do that. I do remember having a hard time understanding some of these topics. So, let's see. I'm gonna play and see if I remember anything, because that was 2 weeks ago.
Now, the thing is
it loud? Feels a bit loud.
When you start to get these bigger networks, potentially you're getting quite a few parameters, right? So I won't ask you to calculate how many parameters there are, but let's remember here we got 28 by 28 input into 100 output, and then 100 into 100, and then 100 into 10, right? And then for each of those...
Oh, wow. On the head. Maybe not. Thanks. Maybe not on the head. I really don't. I do agree that nothing is ever enough, which is a bit sad, isn't it? Yeah, no, I don't work too hard. I think, like, I have this, everybody does probably, but you have this perception of yourself, and you can't get there, and you're like, I don't have a problem of, like, I'm not mean to myself. I love myself, I really do. But I also understand that I could do better, and sometimes it's okay if I don't, and if I do, good for me. I'm not that bad. in the being mean to myself department. I do know that I don't have the energy to do the things that I want every single day, and that's okay. Even if I do them once a week, like, most of the time I'm proud of myself. Thank you.
You've got weights and biases. So we can actually do this. Net.parameters returns a list where each element of the list is a matrix, or actually a tensor, of the parameters for that, not just for that layer, but if it's a layer with both weights and biases, that would be 2 parameters, right? So basically returns us a list of all of the tensors containing the parameters. Num elements in PyTorch tells you how big that is, right? So if I run this, here is the number of parameters in each layer. So I've got 784 inputs, and the first layer has 100 outputs, so therefore the first weight matrix is of size 78,400. Okay, and the first bias vector is of size 100. Okay, and then the next one is 100 by 100. Okay, and there's 100, and then the next one is 100 by 10, and then there's my bias. Okay, so there's the number of elements in each layer, and if I add them all up, it's nearly 100,000. Okay.
Okay, I do remember him, maybe in the previous lesson, doing this manually, so I do remember some of what he's talking about. Maybe.
And so I'm possibly at risk of overfitting. here, right? So we might want to think about using regularization. So a really simple, common approach to regularization in all of machine learning is something called L2 regularization. And it's super important, super handy. You can use it with just about anything, right? And the basic idea, anyway, L2 regularization, the basic idea is this. Normally we'd say our loss is equal to, let's just do RMSE to keep things kind of simple. It's equal to our predictions minus our actuals, squared, and then we sum them up, take the average, take the square root. Okay?
Okay.
So
I'm with you.
What if we then want to say, you know what, like if I've got lots and lots of parameters, don't use them unless they're really helping enough, right? Like if you've got 1 million parameters and you only really needed 10 parameters to be useful, just use 10, right?
By parameters, are we talking about columns or not weights? Definitely not weights, right?
So how could we like tell the loss function to do that? And so basically what we want to say is, hey, if a parameter is 0, that's no problem. It's like it doesn't exist at all. So let's penalize a parameter for not being 0. Right? So what would be a way we could measure that? How can we like calculate how un-zero our parameters are?
Weights and biases? Okay. Use weights that are useful and not weights that are not useful. Makes sense.
Can you pass that to Chen Shi, please, Ernest?
You calculate.
It's like to prevent the model trying to overfit the data rather than fit the rule behind the prediction. Okay, but I think we're being picky with the parameters, so that could even lead to overfitting, right? Let's see.
It's the average of all the parameters. That's my first thought.
Can't quite be the average. Close. Yes, Taylor.
Yeah.
Yes, you figured it out. Okay.
I think if we assuming all of our data has been normalized, standardized, however you want to call it, we want to check that they're like significantly different from 0, right? Would that be
not the
idea?
data, the parameters.
The parameters
weights.
rather would be significantly
And
different.
the
from
parameters
0.
don't have to be normalized or anything; they're just calculated.
Right.
Yes. So significantly different from 0.
Right. I just meant assuming that the data has been normalized so that we can compare them on the same
Oh
scale.
yeah, got it. Yeah, right.
And then those that are not significantly different from 0, we can probably just drop.
And I think Chen Shi's going to tell us.
Line of best fit for noisy data rather than take every point as an oracle to reproduce the okay
Tell us how to do that. You just figured it out, right?
The mean of the absolute value of the.
Could do that. That would be called L1, which is great. So L1 would be the absolute value of the weights average.
Right.
L2 is actually the sum.
Square root sum of squares.
Yeah, exactly. So we just take we don't even have to square root. So we just take the squares of the weights themselves. And then, like, we want to be able to say, like, okay, how much do we want to penalize not being 0? Right? Because if we actually don't have that many parameters, we don't want to regularize much at all. If we've got heaps, we do want to regularize a lot, right? So then we put a parameter here, right? Except I have a rule in my classes, which is never to use Greek letters. So normally people use alpha. I'm going to use A. Okay? So this is some number which you often see something around kind of 1e neg 6 to 1e neg 4. Ish, right? Now, we actually don't care about the loss. When you think about it, we don't actually care about the loss, other than like maybe to print it out. What we actually care about is the gradient of the loss. Okay, so the gradient of that, right, is that, right? So there are two ways to do this. We can actually modify our loss function to add in this square penalty, or we could modify that thing where we said weights equals weights minus gradient times learning rate to subtract that as well, right?
Okay, I followed like right up to here, and then I just lost track somewhere around here. So I'm gonna go back because I lost track and my brain just went to vacation.
So the gradient we actually care about is the gradient of the loss. We don't actually care about the loss, other than like maybe to print it out. What we actually care about is the gradient of the loss. Okay.
What do you mean by the gradient of the loss? Is that a thing? Like the range, maybe?
So the gradient of that
Derivative. Okay.
Right, is that.
Okay. I remember this thing.
Right, so there are two ways to do this. We can actually modify our loss function to add in this square penalty, or
Calculus. Yes. I took it sometime, multiple times. I mean, I probably studied it multiple times, but I took it once in undergrad.
Or we could modify that thing where we said weights equals weights minus gradient times learning rate to subtract that as well, right? Well, actually, sorry, to add that as well. And these are kind of basically equivalent, but they have different names. This is called L2 regularization, right? This is called weight decay. So in the neural network literature, you know, that version kind of was how it was first posed in the neural network.
Jeremy Harris says he's not going to use Greek letters. 2 minutes later. That's actually a good one. Huh. Delta without explaining. Okay. I didn't think it was delta. Like, I didn't think it was a Greek letter. I just thought it's a part of calculus. It didn't, like alpha, okay, but delta, it didn't occur to me that it's a Greek letter. Is the summation thing a Greek letter? I don't think it is, right?
Network literature, where else?
Good eye. Very good eye.
This other version is kind of how it was posed in the statistics literature, and yeah, you know, they're equivalent. As we talked about in the deep learning class, it turns out they're not exactly equivalent, because when you have things like momentum and atom, it can behave differently. And 2 weeks ago, a researcher figured out a way to actually do proper weight decay in modern optimizers, and one of our fast.ai students just implemented that in the fast.ai library. So fast.ai is now the first library to actually support this properly. So anyway, so for now, let's do the version which PyTorch calls weight decay, but actually it turns out, based on this paper 2 weeks ago, is actually L2 regularization. It's not quite correct, but it's close enough. So here we can say weight decay is...
I do remember listening to that part, okay. The 2 weeks ago thing.
1e neg 3, so this is going to set our penalty multiplier A to 1e neg 3, and it's going to add that to the loss function. Okay, and so let's make a copy of these cells just so we can compare. Hope this actually works. Okay, and we'll set this running. Okay, so this is now optimizing. Oh, except if you actually, so I've made a mistake here, which is I didn't rerun this cell. This is an important thing to kind of remember. Since I didn't rerun this cell, here when it created the optimizer and said net.parameters, it started with the parameters that I had already trained, right? So I actually hadn't recreated my network. Okay, so I actually need to go back and rerun this cell first to recreate the network, then go through and run this. Okay, there we go. So let's see what happens. So you might notice something kind of counterintuitive here, which is that
Up, down, down, up, down, like that?
that's our training error, right? Now you would expect our training error with regularization to be worse. Does that make sense, right? Because we're penalizing parameters that specifically can make it better. And yet, actually it started out better, not worse. So why could that be? So the reason that can happen is that if you have a function that looks like that, right, it takes potentially a really long time to train. Whereas if you have a function that kind of looks more like that, it's going to train a lot more quickly. And there are certain things that you can do which sometimes just can take a function that's kind of horrible and make it less horrible. And sometimes weight decay can actually make your functions a little more nicely behaved. And that's actually happened here. So I just mentioned that to say, don't let that confuse you, right? Weight decay really does penalize the training set. And so strictly speaking, the final number we get to for the training set shouldn't end up being better, but it can train sometimes more quickly, right? Yes, can you pass it to Chenchi?
I don't get it.
Okay.
Why making it faster? The time matters? The training time matters?
No, this is after one epoch, right? So after one epoch, and congratulations for saying I don't get it. That's the best thing anybody can say. So helpful. This here was our training without weight decay. Okay. And this here is our training with weight decay. Okay. So this is not related to time. This is related to just an epoch, right? After one epoch, my claim was that you would expect the training set, all other things being equal, to have a
worse error rate. Start the first error rate to the last. This is so different. 1822. Wow.
worse loss with weight decay because we're penalizing it. You know, this has no penalty.
Smoothes the loss landscape. That's a cool way to say it.
This has a penalty. So the thing with a penalty should be worse. And I'm saying, oh, it's not. That's weird, right? And so the reason it's not is because in a single epoch, it matters a lot as to whether you're trying to optimize something that's very bumpy or whether you're trying to optimize something that's kind of nice and smooth.
Okay.
If you're trying to optimize something that's really bumpy, like imagine in some high-dimensional space, right? You end up kind of rolling around through all these different tubes and tunnels and stuff, you know, whereas if it's just smooth, you just go boom. Right? It's like imagine a marble rolling down a hill where one of them you've got like, what's it called? Lombard Street in San Francisco. It's like backwards, forwards, backwards, forwards. It takes a long time to drive down the road, right? Whereas, you know, if you kind of took a motorbike and just went straight over the top, you just go boom, right? So whether, so kind of the shape of the loss function surface, you know, impacts or kind of defines how easy it is to optimize, and therefore how far can it get in a single epoch. And based on these results, it would appear that weight decay here has made it this function easier to optimize.
So just to make sure, it's the penalizing is making the optimizer more than likely to reach the global minimum rather than
No, I wouldn't say that. My claim actually is that at the end, it's probably going to be less good on the training set. And indeed, this does look to be the case. At the end,
That's what I was looking at. It's 22 here and 20 here, even though this started off worse and this started off better.
after 5 epochs, our training set is now worse with weight decay. Now, that's what I would expect, right? I would expect, like, if you actually find, like, I never use the term global optimum because it's just not something we have any guarantees about. We don't really care about. We just care, like, where do we get to after a certain number of epochs?
Okay.
We hope that we found somewhere that's like a good solution. And so by the time we get to like a good solution, the training set with weight decay, the loss is worse because it's penalty, right? But on the validation set, the loss is better, right? Because we penalized the training set in order to kind of try and create something that generalizes better. So we've got more the parameters that are kind of pointless are now 0, and it generalizes better, right? So all we're saying is that it just got to a good point after 1 epoch, is really all we're saying.
I think sometimes with decay produce better models now, but I'm not up on when and how. Okay. I didn't really have much information about weight decay, so it's quite new to me.
So is it always true?
No. If by it you mean does weight decay always make the function surface smoother? No, it's not always true. But if you're having trouble training a function, adding a little bit of weight decay may help.
And so by regularizing the parameter.
Yeah. The one where it produces better models now, I think that's what you're talking about. You're not sure about... You're not updated on the research, I see.
What it does is it smoothens out the loss function.
I mean, it's not why we do it. You know, the reason why we do it is because we want to penalize things that aren't 0 to say, like, don't make this parameter a high number unless it's really helping the loss a lot, right? Set it to 0 if you can, because setting as many parameters to 0 as possible means that it's going to generalize better, right? It's like the same as having a smaller network, right? So that's why we do it. But it can change how it learns. So let's, okay, just one moment, Erica. So I just wanted to check how we actually went here. So after the second epoch, so you can see here it really has helped, right? After the second epoch.
If you see Adam as the optimizer, that means, Adam W. So even Adam has its weight decay version. Okay.
Before we got to 97% accuracy, now we're nearly up to about 98% accuracy. And you can see that the loss was 0.08 versus 0.13, right? So adding regularization has allowed us to find a 3% versus 2%, so like a 50% better solution. Yes, Erica.
So there are 2 pieces to this, right? One is L2 regularization and the weight decay. Right?
No, so my claim was they're the same thing,
okay.
Right? So weight decay is the version if you just take the derivative of L2 regularization, you get weight decay. So you can implement it either by changing the loss function with a squared loss penalty, or you can implement it by adding the weights themselves as part of the gradient. Okay. Yeah, I was just going to finish the questions. Yes, can you pass that to Devesh?
Can we use regularization convolution layer as well?
Absolutely. So a convolution layer just is weights. So, yep.
Jeremy, can you explain why you thought you needed weight decay in this particular problem?
Not easily. I mean, other than to say it's something that I would always try.
You're overfitting.
You could do, and he's a teacher, he should teach options, right?
Well,
maybe
yeah.
solve you.
I mean, okay, so even if yeah, okay, that's a good point, Yannette. So if my training loss was higher than my validation loss, then I'm underfitting, right? So there's definitely no point regularizing, right? If like that would always be a bad thing. That would always mean you need like more parameters in your model. In this case, I'm overfitting. That doesn't necessarily mean regularization will help, but it's certainly worth trying. Thank you, Nat. That's a great point. There's one more question. Yeah. Tyler, do you want to pass that over there?
So how do you choose the optimal number of epoch?
You
just test it out?
do my deep learning course. That's a long story and lots of
You do it by heuristically, or is there any?
It's a bit of both.
Okay.
We just don't, as I say, we don't have time to cover best practices in this class. We're going to learn the kind of fundamentals. Yeah. Okay. So let's take a 6-minute break and come back at 11:10.
I have 15 more minutes, I think.
All right. So something that we cover in great detail, of course, but is like really important to mention here is that the secret, in my opinion, to kind of modern machine learning techniques is to massively over-parameterize the solution to your problem, right? Like as we've done here, you know, we've got like 100,000 weights when we only had a small number of 28 by 28 images, and then use regularization.
Okay, overdo it and then use regularization. Is that the solution?
Okay, it's like the direct opposite of how nearly all statistics and learning was done for decades before, and still most kind of like senior lecturers at most universities in most areas have this background where they've learned the correct way to build a model is to like have as few parameters as possible, right? And so,
I mean, I think there's a branch of modern machine learning where using less resources is encouraged. So don't, like sustainable models. I don't know if that's what they call it, but I know there was a paper on how bad training is for the climate.
Hopefully we've learned two things so far. One is we can build very accurate models even when they have lots and lots of parameters, like a random forest has a lot of parameters, and this here deep network has a lot of parameters, and they can be accurate, right? And we can do that by either using bagging or by using regularization. Okay, and regularization in neural nets means either weight decay, also known as kind of L2 regularization, or dropout, which we won't worry too much about here. So like it's a very different way of thinking about building useful models. And like I just wanted to kind of warn you that once you leave this classroom, like even possibly when you go to the next faculty member's talk, like there'll be people at USF as well who are entirely trained in the world of like models with small numbers of parameters. Your next boss is very likely to have been trained in the world of like models with small numbers of parameters. The idea that they are somehow more pure or easier or better or more interpretable or whatever. I am convinced that is not true, probably not ever true, certainly very rarely true, and that actually models with lots of parameters can be extremely interpretable, as we learnt from our whole lesson of random forest interpretation, You can use...
That would depend on the model, wouldn't it? Interpretability. It just makes it harder to understand it, I guess, the bigger it is.
Use most of the same techniques with neural nets, but with neural nets they're even easier, right? Remember how we did feature importance by randomizing a column to see how changes in that column would impact the output? Well, that's just like a kind of dumb way of calculating its gradient. How much does varying this input change the output? With a neural net, we can actually calculate its gradient. Right? So with PyTorch, you could actually say, what's the gradient of the output with respect to this column? Right? You can do the same kind of thing to do a partial dependence plot with a neural net. And I'll mention, for those of you interested in making a real impact, nobody's written basically any of these things for neural nets. Right? So that whole area needs like libraries to be written, blog posts to be written. Some papers have been written, but only in very narrow domains like computer vision. As far as I know, nobody's written the paper saying, here's how to do structured data, neural networks, interpretation methods. So it's a really exciting, big area. So what we're going to do, though, is we're going to start with applying this with a simple linear model. And this is mildly terrifying for me because we're going to do NLP, and our NLP faculty expert is in the room. So David, just yell at me if I screw this up too badly.
Okay, this is exciting. We're finally getting... Oh God. What was that? What happened? What happened? What happened? Why am I unable to see what happened? Why didn't I get the... Twitch, tell me what happened. Something happened, I don't know what it was. It's my fault for not opening the Twitch, what do you call it? Something happened. There's a thing called the lottery ticket hypothesis, which is like in every high performance, maybe new follower, but I don't think the numbers changed. High performer neural nets, there's like some neurons that is 100th of the whole that's doing like 99%. That would be I don't think it was a new follower. I don't know. Something happened. Anyway, you're saying that okay, now I see what you're saying. There's the 2080 hypothesis where 20% of the effort is going towards 80% of the output, whatever. But like that's a lot. A few neurons doing 99% of the job. I'd prefer if it was 80-20. What happened on Twitch? I really should have opened the stream manager. I thought having OBS open is enough. If someone did something, please tell me what it was. And also, thank you, whatever it was.
And so NLP refers to, any kind of modeling where we're working with natural language text, right? And interestingly enough, we're going to look at a situation where a linear model is pretty close to the state of the art for solving a particular problem. It's actually something where I actually surpassed the state of the art in this using a recurrent neural network a few weeks ago. But this is actually going to show you pretty close to the state of art with a linear model. We're going to be working with...
No, you can specify neural net heaps. Okay, so it's not like a one thing, it's heaps.
The IMDb data set. So this is a data set of movie reviews. You can download it by following these steps. And once you download it, you'll see that you've got a train and a test directory. And in your train...
Is it in the same database? Can I just use that instead of the other thing? Can I start in the middle? Nope, wrong place.
Train directory, you'll see there's a negative and a positive directory.
Ah,
and in your...
for the sentiments, right to right. Where are we? What are we doing? Is this IMDb? How can I find it? Oh, image. Image. Is this lesson 5? Hold up. How can I see the title? Oh, 그래. It is not lesson 5. Shoulda known. Shoulda known. I'm gonna... Oh, hi. 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 Sai? Your name is Sai? Hello, welcome. How are you? I feel like over-parameterization must make things easier for it to learn, though. It's like a whole population, just one person might invent. Yes! Oh my god. And helps everyone. I actually agree with you on that one. Sai, are you the person that I think just followed 5 minutes ago and I didn't see the follow? Oh my god. Coffee Cafe is now like a cheerleader of this channel. Is this useful for WS? Cloud computing in WS. I mean, cloud computing can be done, depends on what you want with AWS. What do you want with AWS? Because cloud computing can be done anywhere, right? If you're asking, can this be run on AWS? My answer is probably yes. Also, hi, how are you? We normally start off chill. Yeah, some fundamentals of machine learning. Wow, I should really answer those things. So, if Sai wants to know what we're doing, we can answer them better. This is a course called Introduction to Machine Learning for Coders. And it's Fast AI, I'm sure you've heard of it. I can send you the link. It's mostly fundamentals. It has 12 video lessons. All of the code is online. You can, use Jupyter. I'm using Kaggle because the code is also there. I will put it in the chat for you. so that you can access it. Data center on land and call it the cloud. Clouds are in the sky. You could probably do it on ISS. It's more than AWS, I think. It's just a course about learning machine learning. Yeah, fundamentals of machine learning. So I hope my title didn't deceive you. Yeah, it's a course about machine learning. Okay. Merci. I'm gonna play the video. No, I wasn't gonna do that. I was gonna see where can I get lesson 5, because this girl's going to skip lesson 4. Let's see if we can find it. Kaggle. Lesson 5. Go. Look at this. How can I not be in love? I'm in love. People are so good. Thanks. Do we need to... this is terminal. Get downloading it. Do I need to... Okay, let's see what Jeremy's doing first.
IMDb data set. So this is a data set of movie reviews. You can download it by following these steps. Once you download it, you'll see that you've got a train and a test directory. And in your train directory, you'll see there's a negative and a positive directory. And in your positive directory, you'll see there's a bunch of text files.
Yes. Oh, wow. It's actually downloading it. What are we downloading? This thing. Everything? Okay. Do that.
And here's an example of a text file. So somehow we've managed to pick out a story of a man who has unnatural feelings for a pig as our first choice. It wasn't intentional, but it'll be fine.
Okay.
So we're going to look at these movie reviews.
Wait, it can just bring out anything? I'm curious what we're gonna get. How big is this data? We're not getting the database, are we? I don't think we are. Or maybe we are because it's already here. Okay, it's already here.
And for each one, we're going to look to see whether they were positive or negative. So they've been put into one of these folders. They were downloaded from IMDb, the movie database and review site.
Yes.
The ones that were strongly positive went in positive, strongly negative went in negative, and the rest they didn't label at all. So these are only highly polarized reviews. So in this case...
So there is no neutral. There should be like at least 5. Positive, negative... somewhat positive, sarcastically positive.
You know, we have an insane violent mob, which unfortunately is too absurd, too off-putting. Those in the area will be turned off. So the label for this was a 0, which is...
very negative.
Negative.
Yeah.
Okay, so this is a negative review. So in the fast.ai library, there's lots of little functions and classes to help with most kinds of domains that you do machine learning on. For NLP, one of the simple things we have is texts from folders. That's just going to go ahead and go through and find all of the folders in here with these names and create a labeled data set. And, you know,
trainings and tests. Got it. Well, that's gonna take a while, isn't it? No? Oh no, it is. Okay.
Well, don't let these things ever stop you from understanding what's going on behind the scenes. Right? We can grab its source code, and as you can see, it's tiny. It's like 5 lines. Okay, so I don't like to write these things out in full, but hide them behind little functions so you can reuse them. But basically, it's just going to go through each directory, and then within that, go through each directory, and then go through each file in that directory, and then stick that into this array of texts and figure out what folder it's in and stick that into the array of labels. Okay, so that's how we basically end up with something where we have an array of the reviews and an array of the labels. Okay? So that's our data.
Okay. It was an array? I thought it was concatenating it. Didn't it look like it was concatenating it? Plus equals? No, it's an array. Okay. Initialized as an array at the top. I'm a life science student. Oh my god. I'm not getting this logics and language. No worries. Yeah, we're in lesson 10. So don't worry about that, because it's all right. If you're curious, you could start from the beginning, because the thing about machine learning is that you can literally apply it anywhere. Any science, it doesn't have to be science. Any major, or God, the thing is going out of my brain. The thing where you say you can apply it to any field. I think the word is field I'm looking for. The course this one's targeted at people, who have computer programming background. You can start here from 0. Yeah, that's true. Or you could just look for something that's more directed at your field of science. There are probably at least blogs, if not videos. But there are a lot of you don't need to understand everything, because even obviously I don't understand everything, and you can still apply things. There's this part. Yeah. What? Yeah, you're lying. This wasn't 99%. Don't lie to me. I think I'm gonna try and end
the
this.
Reviews and an array of the labels.
Yeah. Okay. Yeah. We're in a good place. I really like this. I want to start, inshallah, if all goes well, start again with this tomorrow, because I'm gonna enjoy it. That is for sure. Hello. Scene change. Yes. So this is where we are. This is what we're doing. And I think I'm done for today. Oh my god, it was a follower, and it was the stream manager and our friend, our lovely friend, followed us 10 minutes ago. So round of applause. Clap. Most likely, yes. Highly likely. I'm gonna do my best to do so, and if I fail, I apologize in advance. But yes, the plan is to do that. Thank you for the follow, Sai. I really appreciate it. And honestly, if you have questions that I might be able to answer, I will. One of the things I could do is Google it with you, something like that. No promises, trust me. Trust me. Trust me, you shouldn't trust me. This was fun. Thank you for letting me come here and ramble. and maybe learn a few things along the way. I like it a lot. I have this unattainable goal of streaming. Oh, that's adorable. Streaming every day this month. We're not gonna make it. Yes, if we fail, it's super okay, totally okay. Let's give ourselves a different okay, this is like a goodbye pose. Oh, careful, don't fall. There. Hello. I can change poses, but I have to like do it where you can see me change poses, which is boring maybe. Or I could like go up. I was like, I could go up and you wouldn't see it, but you obviously would see it. So I have to cut out the this looks fun. Hello. I'm learning. See you tomorrow.